All eyes are on the Arctic. Many states are engaged. Most of them are also democratic. There is a lot to be content about. But foreign policy is like Arctic weather. It can be beautiful. It can be dangerous. At least unpredictable. When we head to the mountains, we must be prepared for all weather conditions. The mountain codes are drafted to ensure a safe and memorable trip. These mountain codes are also relevant for Arctic development. Here are the Arctic Frontier's 7 mountain codes for a sustainable future beyond borders. 1. Development in the Arctic must happen on our terms. 2. Trust science. 3. In quest for solutions, the map is our theory, the terrain, traditional knowledge. 4. Choose safe paths. Invest in local communities, technology, and education. 5. Our survival kit is robust infrastructure and collaboration beyond borders. 6. The cookie-cutter model doesn't work in the Arctic. There's no shame in turning back. 7. Always know where you are. Follow these mountain codes and we can build a sustainable future, no matter the political weather. Enjoy the hike. Welcome to Arctic Frontiers 2025 Beyond Borders.
Velkommen til Tromsø og Arctic Frontiers, vår båtdel. Vi møtes her for å diskutere muligheter og dilemmaer. Klima og miljø, handel og utdanning, sikkerhet og beredskap er alle områder som er grenseoverskridende. Her i den arktiske hovedstaden så møtes vi for å løse de store utfordringene. Skaff deg nettverk, bruk tida og finn deg en ny venn. Vi er deres venner og ønsker dere velkommen hit.
Arctic Frontiers has become the place where we gather the most important voices from the Arctic. In 2025, we meet again in Tromsø under the title Beyond Borders. And yes, that might sound a bit strange in a time when the world seems to be building more walls than bridges. But that is precisely why this meeting is so crucial. With increasing geopolitical tensions and climate challenges, we really need to talk to each other. We need to share knowledge, listen to one another, and create hope for a better future. Arctic Frontiers was started 18 years ago by some truly visionary researchers and business leaders. They understood that we must bring politicians, researchers, and the business community to the same table. Because good decisions require insight, not just opinions. In the Arctic, we have always known that we depend on each other. Our extreme conditions have taught us that cooperation isn't a choice, but a necessity. We share knowledge, we build friendship across all borders. I often think of John Lennon's song Imagine, which is about exactly this. Imagining a world where we look beyond what divides us. Let us use Arctic Frontiers 2025 to do more than just dream. Let's take action. I look forward to meeting you. Welcome.
Kjære alle sammen, velkommen til Tromsø, den arktiske hovedstaden. Mens verden rundt oss er i endring, tar vi tak i de store spørsmålene fra Tromsø. Hvordan skal vi leve det gode og trygge liv mens krig, ressursknapphet, klimakrise og naturutfordringer for øvrig er rundt oss? Det svaret må vi finne sammen. Det som virker i Arktis, det virker alle andre plasser i verden. Lykke til med konferansen, og lykke til med alt arbeidet. Takk for meg.
Boris Boetem, on behalf of the Sami Parliament, it is both my pleasure and honor to welcome you all to Sápmi, the homeland of the Sami people. I would, of course, also like to welcome you to the fantastic Arctic Frontiers 2025. Unfortunately, I am unable to attend the Arctic Frontiers this year. As many of you know, the Sami people live across borders in Finland, Norway, Russia, and Sweden. Therefore, this year's theme, Beyond Borders, resonates with us. We aspire to be Sami with as few obstacles as possible from national borders. Tromsø, or Romsa as it is called in the Sami language, is a Sami city and home to many Samis. However, in the past, Norwegianization and border closures have significantly impacted the Sami community in Tromsø, restricting their movement and affecting their cultural and economic practices. Therefore, I highly recommend a visit to the Tromsø Museum during your stay. The museum features exhibitions that showcase both the traditional Sami way of life and the modern experiences of being Sami today. With these words, I wish you stimulating discussions and a successful, enriching conference. Enjoy your time in Tromsø. Kiitos.
Hi everyone, I'm Robbie. I'm helping convene this session today. Thanks for coming, and the room is really full, so I'm really pleased. I had dreams a couple of days ago of me speaking to an empty room, so I'm thrilled. And I won't spend any more of your time talking to you because that was a fantastic video and I can't really compete with it. I just have a few housekeeping things if you want. This is a session based around the IPY, International Science Corporation, so you feel free to get up now if you're in the wrong room, but I'm going to be confident that you aren't. We have 10 minutes per speaker with 8 minutes per talk and 2 minutes for sessions. So speakers, please do keep to that time. I have some threatening looking boards to hold up when you have 2 minutes and 30 seconds left to go. My co-convener Björg can't be here today. So if you have any negative feedback, feel free to direct that to him and not to me. We'll have some questions at the end. We have a roving microphone, so please do wait for the microphone to arrive to you because we also have online participants and they'd really like to hear what you're asking, but they'd also like to keep track of what's going on in the room. So I won't spend any more time talking. We have Heikki Lehavenen talking about the Svalbard Integrated Observing System. Thank you.
Thank you, and good morning, everyone. Nice to see so many of you here. So let me just start to telling you what is SIOS. It's a Norwegian-initiated consortium with institutions who have research infrastructures in and around Svalbard. Currently, we have 25 member institutions from 10 different countries. And it's an observing system or research infrastructure for Earth system sciences. So it's very holistic approach within the Earth system science. And we focus on long-term observations of processes like environmental and climate change. And what I'm going to tell you is based on our own experience in building a multinational, multi-international or international consortium or research infrastructure, and what to also based on our contribution to ICARP IV process. And I hope what I'm going to say for most of you are thinking, oh God, he's telling the same story again, because then I know that our message is getting through. So like the Finnish proverb goes, the repetition is the mother of all learning. Of course, when we have this kind of huge initiatives like International Polar Year, we should ask bold questions. What do we need to know and to do to make the future generations can thrive in changing Arctic as well? How we get politicians involved? And that's a big question for all of us. One of those bold questions could be, for example, water cycle. I mean, it's very vast team, but it's, well, we cannot live without water, and understanding the water cycle now and in the future would be crucial for us, not only in Arctic. Well, what happens in Arctic won't stay in Arctic like a sea level rise because of the melting glaciers. And there are multiple different kind of effects with the changing water cycle. So we need to identify what are the key co-variables we need to start to observe in order to understand the future. We need to think big, but we need to also act together. We all know that Arctic systems are interconnected. So in order to understand, we need interdisciplinary approaches. And also interdisciplinary approaches, not only in natural sciences, but we need to involve social scientists, humanists, different interdisciplinary in order to influence politicians. One example, what we have experienced to be very, very good, what comes into interdisciplinary science is actually share the data. We need to share the data so that it's visible for all. So we have a science data management system where all the science members can provide the metadata. So then you can filter down what is measured, different parts of the archipelago, so you can make the connections just by digitally in your own laptop. And it's open and it's free, our database. So that should be applied also in the coming international polar years. All the data would be shared, need to be shared. We should work smarter, not necessarily harder. So we really encourage co-location of observations to focal sites from multiple disciplines. It's amazing how many good initiatives comes just out of when people are working in the same research station from interdisciplinary approaches. New Ålesund is a good example. A lot of new initiatives have just come up because people are sharing dinner table or dinner and coffee breaks. Work smarter, not necessarily harder. We need to minimize duplication. That's already what comes to decrease the environmental footprint of science. So how we have approached it, we have our own catalog, observation facility catalog, where we know what people are doing in different parts of archipelago. Similar should go also for IPY. So we actually know, everybody knows what is happening in the Arctic, or in our case in Svalbard. I need to check if I have some. Yes, we have our own the state of environmental science in Svalbard report. The last was published last week, and it gives recommendation. What are the knowledge gap? What do we need to know? What do we need to observe in order to understand what is happening in Arctic? So our research infrastructure is dynamic in the sense that we adapt all these recommendations in an annual cycle. And in order to get these coordinating interdisciplinary studies, it's not always so simple. You need to push a bit. You need some strong coordination in order to get this kind of interdisciplinary approaches. For example, projects that actually you have to have different disciplines involved. And our mission statement is something that could be actually adapted also for the IPY process. There are key elements. There's data sharing, decreasing the environmental footprint of science, sharing infrastructure, and facilitating interdisciplinary research. Lastly, I would like to take you back to third International Polar Year in 1957. That is also called, well, it was promoted to International Geophysical Year. It's often referred one of the most significant scientific collaborations of the 20th century. And it happened during the deep Cold War era. My deepest hope, honest hope, is that the geopolitical tensions will decrease, war in Europe would end. Of course, I would like to all the war ends, but the geophysical tensions need to be relaxed. And then science and science diplomacy can lead the way to safer world and Arctic. I leave it here.
Thanks. Is SciAS already affected by war in Europe, would you say? And if so, in what ways?
Yes, it is, as you know, in Svalbard. Well, I don't know if you know, but there is two big villages. One is Longyearbyen, which is Norwegian, and one is Barentsburg, which is Russian. And of course, due to this war, all the collaboration between these two towns have deceased. So it's affecting, and we don't have any collaboration with Russian institutions.
I do have a cheeky follow-up. So in what way does that actually impact the observations that are being made in Svalbard?
It doesn't affect so much observations that it made in Svalbard. Of course, it affects all those institutions that has been collaborating together. I think we should be more concerned about the half of the Arctic being more or less non-accessible in many ways. Thank you.
So we now have Jonathan Cohen, who's going to speak to us about another great project that's happening in Svalbard, ArcLight.
Thank you very much. So I'd like to start by acknowledging some collaborators. So collaborators at UET, NTNU, as well as the University of Strathclyde in the UK. And I'm speaking on behalf of this ArcLight project funded by the Norwegian Research Council that's been supported as well by staff at Kings Bay and NP in terms of logistics support. So let me start by discussing a problem. So this problem has to do with light. And so we know that light is an important ecological factor at high latitudes. And it's just throughout the year. Even when the sun is below the horizon, that diffuse light during polar night still has biological implications. And so this has come up, it's cartooned here with all of these biological processes that are influenced by light. So it's a very important ecological factor throughout the year. The problem, though, is that when you think about the sorts of instrumentation that's used to measure light in meteorological arrays, I'm thinking about the baseline surface radiation network and pyranometers that you see up here. This is the sensitivity of a pyranometer shown in the black line. And then in the little rainbow colors inside, I have the sensitivity of a fish visual system. And so when you have biological questions, it's very difficult to use these kinds of light information to really get at understanding those biological data and how light is available to these organisms. And so we have this problem, a wavelength problem. There's also an intensity problem. And the intensity problem is that if you take a look at light data from a commercial light sensor over the course of the year, there's these two sides of the graph right here that are showing you when there's just not light that the sensor can detect. So the light is too low for a typical commercial sensor. And so with these problems, this wavelength problem or color problem and this intensity problem, we need new solutions. And so the solution that we've come to in this project has been the ArcLight Observatory on Svalbard. So just as we heard in the last talk, these ideas of sort of co-locating science, this is an example of co-locating science in Ny-Ålesund. And so what we've got in the ArcLight Observatory, which you can see here in the figures on the right, was really born out of an international collaboration. It came into collecting data in 2017 and has been going ever since. And it's an international collaboration, Norwegian, UK, US partners, to try to understand biological questions that revolved around light. And so we realized very early on that we didn't have the light measurements we needed to really get at those biological questions. And so you have ArcLight that came out of that. And so what we've got is a focus on the biologically relevant light, as I mentioned in those previous slides, that we need to think about light in a way that's really biologically focused. So thinking about the electromagnetic spectrum, the visible light, 400 to 700 nanometers, violet to red light. And so at the core of ArcLight, I just want to talk about the sensors a bit, is a digital camera with an all-sky, a fisheye lens to give you all-sky images. These are shown here on the left. You can see polar nighttime, you can see midnight sun time, you can see our pollution in the bottom left corner, you can see aurora borealis on the bottom right corner, so all kinds of ways. And beyond pretty pictures, though, what's important about this camera is it's calibrated to be able to integrate light across the whole camera view and get a single value that gives you a photosynthetically active radiation light measurement, and radiance of PAR, it's called. Right? And so if you look at the plot on the upper right, we see a year and a half's worth of data. If we go into the polar night period, you can still see this oscillating up and down, these daily patterns of light, and you see the periods of the full moon. If we go in again to that middle region, you see the full moon, the new moon, the full moon again, and you can see that arcing pattern. But even on the daily cycle in the middle of the polar night, you still see these daily patterns. So there's light there. We can now calculate. We can measure it. There's other sensors as well. We've got hyperspectral irradiance sensors that are measuring those wavelengths in more detail. And I sort of slipped over this on the last slide. That camera is measuring at 1 hour intervals. So this is a very high resolution. And then these sensors, the hyperspectral sensor, for example, the one that's giving you those different wavelengths, is every 20 minutes. That peters out for about 2 months of the year, so we don't have that sensor. And then other commercial sensors like this LICOR sensor is giving a measurement comparable to the camera. But it also has about 4 months where it doesn't work. Temperature and relative humidity sensors, as well as experimental sensors to give us an opportunity as a test bed for new sensors, either commercial or ones that we prepare. All these data are available through the NERD research database as well, so they're publicly accessible. So I wanted to mention a few applications of what we've been doing. And so some recent applications of the ArcLight Observatory has been through this radiative transfer model, Heimdall. So it's a light field model that lets you determine what the light, spectral composition, and irradiance is underwater. So we've got atmospheric light measurements at ArcLight, but this is a way to expand that in a pan-Arctic and, in fact, global frame. And what we've been able to do with ArcLight is be able to calibrate it and develop that model to work during the polar night very effectively. And so it's been a great way to extend this point measurement of light to a far greater scale. We've also been able to take these data and understand how organisms interact with each other. So breaking out that light underwater into the spectral components, so driving the light into the water and breaking it up. We've been able to ask questions about migration, about predator-prey interactions, as well as chronobiology questions, biological timing questions, all of this because we have very solid light measurements throughout the year and a way to interpret them beyond those point measurements. And then lastly, breaking up the light into different colors, which this camera can do and our other sensors can do. We've been able to ask questions about spectral change, color change of light throughout the year as you move through times with ambient light, artificial light, as well as aurora borealis. And so thinking forward, what we've been talking about and thinking particularly about IPY would be to think about how to scale this array into smaller packages that can be placed elsewhere. And the core framework that we have in ArcLight is straightforward to do that. It's just a matter of funding. The other thing that we've been thinking about is taking in new sensors, and we've been doing this. So as new commercial sensors become available, or as we've also been developing new sensors, this is a test bed for new equipment that you might want to deploy. And so we have a very solid record of light, and if there are new sensors that are being developed that you have an interest in deploying, this is an excellent, again, test bed against which we have a solid light record. And then finally, the idea of having underwater light observatories, obviously the data we collect has terrestrial applications as well as underwater applications, but to get more solid underwater data throughout the year is a real goal. And so the potential for developing an underwater light observatory parallel to the terrestrial arc light observatory is an interesting option and something we want to pursue. So with that, if there's time, which I hope there is, I'll take some questions.
Thank you. Very interesting presentation. I was wondering, have you been able to link the light you've measured already to certain biological processes?
Yes. So we've been able to take the light and we've collected a lot of data, both sort of physiological data from visual systems as well as process data, photosynthetic process data, and have sort of mapped out the levels of light where those processes are starting. So that's one way we've done that as an introductory point, is to say, okay, this is the light field, and then this is in the atmosphere, this is in the water, and we've measured a lot of optical properties of the water to also improve those models. And then relate that to the sensitivity of human vision, sensitivity of fish vision, sensitivity of krill vision, how photosynthetic processes work in kelp and phytoplankton and such. So that's the way that we've initially done it. And then also predator-prey interactions. We have a few papers that have modeled that light and looking at those interactions. So yeah, we have a series of papers, which I'm happy to share with you afterwards, that get at those questions.
Okay, very interesting. Thank you.
Mm-hmm.
A slightly technical question. I was amazed that you have this amazing full moon signal. I'm surprised that that wasn't masked by cloud variability. But then it made me wonder, to what extent is this observatory representative of the ocean, of the Barents Sea, of the high Arctic? Because it's based on land, and I imagine that might affect things.
Yeah, and so when we do, so I showed you that sort of Barents Sea map of light. So cloud data come into play there. So you definitely, the clouds are observable in that, and if you look at cloud cover, you can see that signal in the light observatory, as well as a slight signal from Neolison itself. So there's that you have to worry about. So those are issues, but you can get around it, I guess, in a larger scale. A larger scale modeling framework by including things like cloud data. And that's all built into the Heimdall model. Okay.
Thank you. I was wondering, do you separate artificial light and light pollution from the natural light cycle?
So we can do that in the hyperspectral imagery, or the hyperspectral camera, because there's a separate instrument. In the hyperspectral radiometer, we can disentangle the artificial light, and we're working also to implement that in the camera images as well. And so it is an issue, but you can figure it out spectrally. Thank you so much.
So we now have Hannah Sagan going to talk to us about the High Arctic Ocean Observing System.
Thank you very much for letting me talk to all these people about what is my passion in the Arctic. I'm not part of the Arctic passion, but I still have a passion. So I will talk about how to engage the industry, because in Norway we have a fantastic group, or not group, but a community of subsea technology companies, and I think that we should benefit from them to build a robust system that can observe the ocean under the sea ice. So I want to talk about HEAUS, which is implementation of a system. I want to talk a little bit about AOS, which is more on the plans for the future. So, first of all, why do we want to observe the interior of the ocean? And what are the challenges in doing so? And how can we benefit from the subsea industry? It's so good it's down there. So, I guess you have seen this map from Agnieszka before. It is about the circulation of the water masses in the Arctic Ocean. It starts with the inflow through the Fram Strait. It circulates around the Arctic, and it stays there for up to 25 years. So we need to have a long-term perspective when we establish an ocean observing system, not only spot measurements, but really have a long-term perspective on what we are doing. So, multidisciplinary research is another aspect. You should not only focus on one thing, we have to have an integrated view on what is going on under the ice. The physics, the biochemistry, and the biology. And of course, these models that we have, they need data to, to be calibrated so that we know that they predict something that is true. And you can see the large spread in the model, which is critical to take a look at. And also we have another thing, and that is Greenland with the ice melting, and you can get increased seismicity and also other geophysical events. So we need to have a long-term perspective in our observations. And how do we do this? Today, we have a lot of tools to observe the ocean. We have satellites, which only get the surface. We have surface buoys or ice buoys, which can have instruments below the ice. And this provides us important information in real time. Then we also have AUVs, AUVs that is too expensive, I think, for most of us to put under the ice. We have gliders which we are reluctant to put under the ice. We have moorings, which I will talk more about. But the most important is still the buoys that have instrumentation below the ice, because it sends data back in real time to ocean models and to climate people, researchers. But the problem is the low coverage. And most of them are on the US side and very few on this side. And this is also because when we deploy something here, it will go out of the strait. We have Argo floats, which cannot provide data with geoposition when they are under the ice. It will be prohibited to send data via satellite and also to get its position. So Argo floats is still a little bit difficult to use in the Arctic. Therefore, in HEAUS, we have set up a navigation system, or not a navigation system, but geopositioning system with sources so that you can position your underwater visuals or floats. And this we are going to test this summer with buoys and also with some floats. But these moorings have issues. It cannot deliver data in real time. You have to take it up and then download data. And that is one of the main challenges we have today, is that the data access, you have to be patient. You have to wait for 2 years, maybe 3 years, if you don't get the ship time to get it up. You have limitations in power supply. You have growth on the instruments, calibration issues, and of course, long-term funding. So there is issues with the moorings, and this is where we really want the industry to come and help us, or that they want to work with us. And that we do in HIAOS. So this is the system that we put out this summer, and it will be out for 2 years. So 4 moorings, and there is 2 moorings from the Polar Institute. So I think this is the first time we have so good coverage with moorings in the Arctic. And we are having them out, as I said, for 2 years. And we are looking very much forward to see what comes out of it. Then the Swedes, they have a nice project which we work together with, Polar Connect, and they plan to put the cable across the whole Arctic. And that one will be observing system, but also provide capability to communicate data in real time. So what we are working on in IOS is to work with the industry to look for possibilities to connect mooring systems to the cable. And it can be either direct connection with cables, or it can be AUVs that goes and pick up data like a messenger. So there is a lot of potential here, because this is things that it's already developed in the North Sea, for example, where you have subsea installations. So this is really something that we hope to be able to do, because now you have this system on the way, and then this one is in water. So linking these 2 systems is what we really want to do. Examples of involvement is that the industry is involved in digital technologies. They are involved in sensors and technology. And one of the things is to pick up data from the sensors. And Sticker is a small company in Stavanger who have been engaged in this. And this summer, we will do the first test under the ice with this homing ROV system to collect data and also to charge the batteries. And what is nice to see is the engagement in the industry to do this, because they see the potential of using it other places. So an integrated and sustained underwater observing system need collaboration with the industry. And it needs to support also multidisciplinary research. And I think we have a unique position here in Norway. We have strong research communities, and we also have strong subsea industry, and we should work together. And I think that this is one of the things that could be an IPY thing, is that we could involve industry more than we have done before to use state-of-the-art technologies. And it will be important to start now the observing, not the international year, but now. So thank you very much. Talk to me afterward.
Yeah, we've run out of time for questions on this talk, but yeah, please do catch up afterwards. That was actually my fault. I was so mesmerized by the video that I forgot to hold up these things. So we now have Åshild Petersen talking about the Svalbard tundra. So back to Svalbard for another talk.
Thank you. Yeah. In this talk, I will introduce you to the Climate Ecological Observatory for Arctic Tundra. And I will also speak about how we can contribute to the next IPY. And first and foremost, I will say COAT is at the core of the SciA's work on the Svalbard tundra. Next. Okay. COAT is focusing on the low and high Arctic Svalbard. In this talk, I will focus on Svalbard. I lead COAT Svalbard, and in this region, the temperature increases are up to 5 to 7 times larger than the global average. COAT is ecosystem-based. It's a direct response from the Fram Center institutions for an international urgent call for scientifically robust observatories. We enable real-time detection, documentation, understanding, prediction of climate impacts on the tundra ecosystem. In this respect, we provide a basis for being prepared, being able to adapt, and to take action. Giving you a little journey of the COAT, it started many years back, starting in 2010 with the first building blocks with Norway's ambition to become world-leading in climate and management research of the northern environment. Inspired from the IPY in 2013, we published the science plan that gives the overview of the whole system. In 2015, we came on the Norwegian road map for research infrastructure and started the implementation of research infrastructure with the help of the Norwegian Research Council and SciAS. 2021, the first proof of concept, we evaluated the condition of the ecosystem on the Arctic tundra using the data. 2024, we came on the state budget and was given funding for the long-term operations. 2025 launched as a research center at the UIT and now moving into eternity and with an important stop in the next International Polar Year in 2032. Okay, COAT is a ready rigged observation system. It's climate-based with state variables related to weather, climate, and physical processes. It's ecosystem-based with state variables related to climate-sensitive species and functional groups. It's science-based with hypotheses, models, methods, and state evaluations. It has its own infrastructure co-located with its own study design integrated into the SciAS framework. Its end user has focus on end users with its own protocols for how to involve end users. And it has a framework for outreach. So it's a ready rigged observatory up and running and operating. We apply a food web approach which was inspired by the former polar year with examples from the Bylot Island in Canada and Greenland. We cover in Svalbard 5 biotic modules and a climate monitoring network that overlays the tundra food web. We have developed a common set of climate impact path models that guide the monitoring. It's climate-sensitive targets, and it's building on and enhancing the already ongoing long-term monitoring that we have on Svalbard. It outlines a set of a priori hypotheses for the key processes and relations, and it's adaptive, so it has a continuously updating and changing when we gain new knowledge. And climate and management are the main drivers of these relations. COAT also provides tools for parameterization of statistical versions of the path models. So in this sense, we have the ability to provide a framework for causal inference, both estimation and attributions, about climate impacts, management options, and ecological forecasts. COAT developed its own research infrastructure. It's covering Brøggerhalvøya and Nordensjøland with a set of infrastructures co-located with a common study design that allows a common analysis and common use of the data. And it covers the wide and existing types of gradients that we have on Svalbard, both when it comes to coast inland and also from lowland to higher elevations. And the instruments and the study designs facilitates the ecosystem-based monitoring. We have access and give access to study designs and measurements of a multitude of integrated ecosystem or ecological questions. There is also a possibility to link short-term experimental studies, for instance, with long-term monitoring. COAT have established an extensive climate network, a monitoring network that adds to the existing stations, 8 new stations that cover the coast inland gradient, and a total of 17 meteorological stations with open access data live for everyone. We also have a digital infrastructure that's common for both study sites, both Varanger and or Finnmark and Svalbard, and it's compatible with what SIOS have set up. And with that, I will say thank you.
So first, congratulations with being on the state budget for COAT.
Tusen takk.
So I was just wondering, you said that you were inspired in 2010 by the setup in Zuckerberg and in Canada. So what, for the next polar year, what could be the pan-Arctic view and collaboration for COAT?
I think the setup really facilitates the cross-ecosystem analysis and working together. So I think what we have built up, the kind of framework, would enable us to set up similar types of observatories built on the same way of thinking, because a lot of thinking has already been done. And like I said, it's been Bylot Island and Zuckerberg have been very important and was a main driver of getting things going back in time in 2010. Yeah. Yeah, okay.
Okay, we now have Jørgen Berger to talk to us about Polhavet 2050, which is a major plank of Norway's IPY strategy, I think. So, Jørgen, over to you.
Thank you very much. And thank you for the opportunity to present to you Arctic Ocean 2050, or Polhavet 2050, as we say in Norwegian. It's a large national initiative based with 18 national partners, all listed here. I won't name them, you see them. Polarhavet 2050, Arctic Ocean 2050 is based on the massive changes that are occurring in the Arctic Ocean. We who live today, we are likely to be the first modern human beings to witness an ice-free Arctic Ocean. It changes from an ice-covered white ocean to open blue ocean. It's a massive and dramatic change. And also, it's been said before, what happens in the Arctic doesn't stay in the Arctic, but also what happens in the Arctic doesn't necessarily originate from the Arctic. Quite the opposite. Changes in the Arctic and the Arctic Ocean is connected to global changes, ocean currents, weather systems, climate systems. So understanding the Arctic Ocean is not only important for managing a changing Arctic Ocean, it's also important to understand how climate change affects the planet. So what we are in the process of planning and setting up is a national initiative to study these changes. We want to implement a full observational pyramid ranging from satellites, airplanes, drones, vessels, autonomous platforms and vehicles, and subsea observation systems like the ones we just heard about from Hanne. And also take a multidisciplinary approach in order to study and understand these changes. So everything from geopolitics, business, international law, climate, ocean science, ecosystem science, and energy are themes that Arctic Ocean 2050 will cover. We have made a funding plan for this. I won't take this opportunity to go into details about the funding plan, but I want to raise a few important issues. It's a 10-year program. We aim to start 1st of January next year. And we ask for a total of 100 million Norwegian kroner per year in fresh funding. The 18 institutions involved, they will come up with a similar amount in own contributions during this period. So in total, the total budget on average is 200 million each year. But as you see here, it covers the International Polar Year, and we foresee that the activities will increase during the International Polar Year, hence also that the amount of funding and activity levels will increase during that period. It is a Norwegian initiative, but the Arctic Ocean is not a Norwegian ocean. It's quite international, and it has strong connections. Many of us tend to think about the Arctic Ocean as something that is remote and isolated, but quite the opposite. It's a node in ocean circulation and also in climate and weather systems. So in order to understand the Arctic Ocean and the changing Arctic Ocean, it's impossible to do that simply from one sector of the Arctic Ocean. We, as a national initiative, we will of course base our project and measurements on the Norwegian part of the Arctic Ocean, but it's important to provide and make sure that there are strong international connections. We hope that this will be a node and a sort of an umbrella for the international activities and focus on Arctic marine research during the IPY in order to combine national initiatives from Norway and other both Arctic nations and nations interested in Arctic research. So that is a quick summary of what the Arctic Ocean 2050 is. Again, 18 Norwegian institutions, all listed here, and also with a homepage where you can get further information. Thank you.
So we now have Volker Rackold to tell us about lessons learned from the Arctic Passion project. Thank you.
Yes, thank you very much. So this is a presentation from the Arctic Passion project. It's a European project dealing exactly with things that were already discussed here, observing system. So it's, and I want to start actually going back to the last IPY, because all these discussions we have today on observing systems and what we need to do started actually in the last IPY, actually in the IPY 2007 and 2008, when we realized better, in order to understand the Arctic, we really need an integrated Arctic observing system, which provides us with the necessary data that we need for projections, for scenarios, for everything. And this refers to everything. So this is a really an overarching idea of having broad Arctic observing system, or kind of a system of systems, where all these networks that we already heard about are integrated and getting together so that we have access to all this information that we need. And that was the idea that I think it came up during the last IPY in 2007 and 2008 from various, let's say, arenas. So it came up from the science, but it also came up from the Arctic Council, from the political arena, where people realized we need something like that. And we had many discussions on that. And eventually, the thing that we created, and that was Arctic Council and the National Arctic Science Committee together, was SAON, Sustaining Arctic Observing Networks, which was the idea of having a mechanism or a body to coordinate everything that's going on in observing systems in the Arctic. So, and SAON started in late of 2007, 2008 or something like that. And since then, we have been trying to really move this forward and really to develop those kind of things. And it was actually also, there was another idea that came up that was an Arctic Observing Summit that is organized now every 2 years, where we get all the people interested in observing together, and SAON and Observing Summit then later join forces to make this one approach towards an observing system. So, and then of course I should mention the Arctic Science Ministerial meetings. There were 3 of them, the first in Washington in 2016, then there was one in Germany in Berlin 2018, and a third one in 2021 in Japan. And they always mentioned, the ministers always had the statement that we need a circum-Arctic observing system. So the need is there, and of course now, seeing where we are now and looking toward to the next IPY, we have to see where we are. So I think one important element that came in through funding of the European Union was first Intaros, and then, and that's what I'm speaking about today, Arctic Passion, so European-funded projects. Of course, these are 5-year projects. They are well-funded. Arctic Passion has a funding of something like 13 million euro for a certain time period, but they are projects. And of course, the question is what happens when these projects are over? And I think at the end of the day, what we want, and that is what my hope is, that by the next IPY, we have something up and running that we can do all this kind of work. So in my next few minutes, I will tell you a bit about Arctic Passion, the Arctic Passion projects, and recommendations that we are developing towards such an integrated observing system. So what has to happen so that we have it in place in 2032, 2033. So Arctic Passion, as I said, is a European-funded project with something like 40 partner institutions from many organizations in Europe, and a very strong contribution of Arctic indigenous peoples communities. So we cover 18 countries. We are very well connected also to North American counterparts. And we are now entering the final year of Arctic Passion, and that's the time when we think of what do we recommend? What do we recommend to people of what has to happen? So what Arctic Passion is doing, of course, we are covering a broad range of things. Enhancing instrumentation, inclusion of different knowledge systems. I talked about the indigenous peoples involvement already. Developing new services. Data systems are important to Arctic Passion. We have a very strong component on data systems. We have some new services that we organized and started, or we started them as pilot services. There are now new services now for people living in the Arctic. We use, of course, the SAON concept on the shared Arctic variables. And of course, we look into making things is important for for societies, so social benefit assessments. And of course, international collaboration, that's really important. As I said, we have very good connections to North American counterparts of Arctic Passion. So, and of course, that's actually what we are doing at the moment, is providing advice to policy and providing advice to decision makers. Because at the end of the day, we need that link to the policy if we want to do observing systems in the Arctic. So, and of course, contributing to developing a clearer and more equitable international structure of an observing system. So what we did in preparation of Arctic Frontiers, we organized a survey within Arctic Passion, especially addressing the funding agencies. So there's one body which is called the Arctic Science Funders Forum, which was born during one of the Arctic Science Ministerials, and that's a network of the funding agencies. And of course, at the end of the day, the key element of such an observing system is the funding. So we organized a questionnaire, and we talked to people and tried to find out what are the main recommendations that we can give to funders. And we came up with 3 groups. One is governance and coordination, one is observations, and one is data, with pretty clear recommendations of what has to happen to have such an observing system in place for the next IPY. So, and what came out, I'm just going through these recommendations to show you where we are. So we need better support for SAON, that's clear. So SAON has been working for a long time, and we need a better support for SAON. We need a long-term commitment for a governance system, and we talked about the European Polar Coordination Office and the North American counterpart. We need enhanced sharing of research stations and infrastructure. One example is Interact, for example. Equitable inclusion of indigenous peoples, I already talked about that. In terms of observations, one key element is we need long-term funding for long-term observations, and that's the problem with project funding because it's not long-term. And we need the monitoring must be based on societal needs. Regarding data, improved data handling and provision, applying fair and care data principles, and improved integration and use and sharing of data. So at the end, we came up with a list of recommendations or list of things that we need to do in order to have such an observing system in place for the next IPY. I think I'm not running out of time. I have 2 minutes. So just go quickly through this list of recommendations that we need for the IPY. So I mentioned many of them already. So increased integration and cooperation of a multitude of observing programs. So we heard many examples today, and I think we need a mechanism to get all of them together, to get all of these together and make the data of all of these available for everyone in one system. So a more holistic approach, so inclusion of different knowledge systems. We talked about indigenous peoples' involvements and indigenous knowledge involvement. More action to make the observing system useful for diversity of people, so make it useful for society, that's important. Stronger inclusion of indigenous knowledge, I already mentioned that. We need a good data structure. We need to make sure that the data are available, that people can use the data. We need sustained communication channels, very important. And the most critical thing, I think, at the end is, of course, we need sustained funding and political support for, at first, user and research-driven observations, long-term, which is very important, and then, of course, for better coordination and equitable and inclusive governance structure of such a system. So these are the things that we came up with, and we will have a workshop here with the Arctic Science Funders Forum, which is unfortunately by invitation, so it's closed, so I cannot invite you to that workshop. But we will discuss these recommendations with the funding agencies, and we are very pleased to see that many funding agencies are showing up, and we have a good audience, and we will find out and see what kind of things are possible until the next IPY, hopefully having such a system in place when we start our work for the IPY in 2032. Thank you. There was one. Yeah.
I take the opportunity to ask that single question. So for a very long time, you know, the research community has worked to establish observing systems. And now there's all this talk about integrated systems. So the INTAROS, was a contribution to establish an integrated Arctic observing system. Arctic Passion thought, no, we cannot build an integrated Arctic observing system. We need to build an Arctic observing system of systems. And so my question is, how realistic do you think it is to build one integrated Arctic observing system of systems? Wouldn't it be more realistic, you think, to build integrated Arctic observing systems of systems? It's obviously a limitation, you know, how far you can get and how operational you can be.
It's a good question. It's a good question. As I said, this is a long story. So it started in the last IPY, maybe even before that. We thought, ideally, and that would be my dream for the next IPY, that at the end of the next IPY, we come in with one, let's say, one entry point to Arctic data and observations. So whatever I need, I find one place where I get everything. And that would be my dream. And that would be, I think, the ideal thing that we would have maybe after the next IPY, to that people, everyone, and it's in a way that everyone can use the data. And that's, I think, that's the basic idea, the fundamental idea behind it. It's maybe a dream, but I think we have to work towards that. Thank you.
Thank you. So we now have Michael Gallagher is going to tell us about an in situ project that links into fair and care principles.
Hi, everybody. I think that's a great dream. I really admire it, and it's a great introduction to the type of work that we're doing, and I hope we get there also. Let's see, next, great, and we're down here. So I titled this talk Towards a More Autonomous Future, and it's about a very specific project, but the idea is that there are these research stations, places like Svalbard, that do these amazing things and are a really important part of observing, but that we also need to be able to build smaller, more portable things that we can take strategic observations with. And this is a small list of collaborators that I work with, but the reality is that this is a long-running thing that has been funded by multiple institutions over the last decade to create these types of technologies. So I have a very specific perspective. I know everyone in here is not interested in these detailed things like boundary layer characteristics. I think about where the atmosphere hits the sea ice or Greenland or these sorts of places and the ways that the energy and precipitation and other things exchange. But I'll try to keep it very general, and my interests are kind of diverse. It's not a talk in the 2020s if I don't mention machine learning at least once, and I'm talking about science, but this is about the autonomous observations and renewable power systems and the things that we can use to create these observations in places like central Greenland. But I'll try hard to stick to a broad appeal for everybody here. My vision for IPY is related to the autonomous observations. It's that if you don't take good in situ measurements, then you can't have a ground truth for critical science from satellites to models or these really important things like projecting into the climate future. And those observations and the data that comes out of them need to be numerous and diverse and of the entirety of the coupled climate if possible. So you create this platform and you want to know how energy goes from the clouds all the way into the subsurface on the ice if you're taking measurements at that specific point. And ideally it's fair and open source. You get that data to a platform and people can go there and they know where to get it and they know how to use it and there's the appropriate metadata so that someone who doesn't know exactly what you're talking about can at least interpret it or contact you. And so our team made a modular platform, and it's a complete in-house prototype from beginning to end to do that sort of thing for the in-situ coupled climate observations. It's a custom renewable power system, so those boxes on the left that are all shiny with a bunch of wires are battery packs that we built that are roughly half the size of a Tesla battery pack. So there's a lot of power inside of this so that we can power things like lasers and radar to make measurements of cloud and ground penetrating radar to make measurements of the ice. And it's plug and play. People have mentioned sensors and making prototypes for new things. The idea is that if you do really good at this, it's kind of science Legos. Somebody can come to you and say, hey, what if we add this onto that? Or could we use that for this? For something like IPY, that's a really great thing to be. And it's probably, in my opinion, the most important part of making this. So this is what that looks like. This was from this summer. So we did all of that and we installed it in the melt zone in Greenland. And it's a whole lot of solar panels and wind turbines and this platform that has all sorts of things attached to it. There's lasers, there's radar, there's precipitation measurements and wind and subsurface measurements of temperature. And we did a lot of other things like snow pits and auxiliary measurements. And if you scan that QR code, there's a video online. This particular project, the most recent iteration, was called ICARP MELT, which had a fancy acronym for measurements along Lagrangian transects. The idea was to connect these sorts of autonomous measurements to where we have a research station to verify them. So the blue dot is Summit Station in central Greenland. The red dot is where we installed it, where it actually melts semi-frequently. So we installed all of these observations, and then we made measurements in the melt zone to connect to fancy things like mass budget and precipitation and things like that. It's about 140 kilometers from the coast. So it's, for something like this, that's very, very close to the coast, and it's where a lot of the critical things are happening in the Greenland ice sheet. The science points, the really important things that we were interested in characterizing for this single summer, were clouds before they get up onto the ice sheet, which are a very important part of the energy budget in Greenland. The near surface atmosphere, so profiling as best as we can the lowest kilometer of the atmosphere, and then relate that to how it couples with the surface. So all of these things are going on in the atmosphere, but what happens at the actual surface, and how melt events evolve, and how that relates to things like atmospheric transport, where that energy comes from. Oh, I wondered if the video would work. That's fine. This is supposed to be a video, but we had a whole camera system strapped to this for the entire summer. So we had a skyward-looking camera that had a full field of view, fisheye, and then we had monitors for all of the systems. And we got all of these variables back in real time. So we were able to transmit and package the data in a way that someone who does things like forecast validation could get that data and evaluate it the day after that we take it. We had this sub-module called ASFS that did the surface fluxes, so things like complete broadband radiation, incoming diffuse and direct, meteorology, turbulent fluxes, and then we had Föhn measurements in the subsurface, the temperature strings, radar reflectivity into the subsurface to retrieve things like the evolution of density in the subsurface, and then a bunch of other observations that were auxiliary to that, so these measurements of the clouds that I'm talking about with lasers and radars. Oh, I needed to click once. Well, it did work. The power system, we called it the MVP, the minimal viable power system. It doesn't look very minimal to people who do things like buoys in the first presentation, for as large as it is. But the reality is that you need that kind of power to run those kind of instruments autonomously. There's some statistics there. It's 30 kilowatt hours of storage, 8,000 watts of solar, which sounds like a lot. This was a test, so the idea was that we could make it quite a bit smaller in the future. And then it's not science if I don't make plots, but we had real-time feedback for the power system. So things go wrong in places like Greenland, and you want to know exactly what sort of power you're getting, so you can do things like turn off your lasers if you're starting to run low on a battery pack. So these are some highlights. It's very preliminary. It was only 6 months ago we were out on the ice sheet doing this work. But we need some science plots to talk about to make it even more official. So that plot on the right is a fairly simple plot that's supposed to relate the atmosphere to the subsurface. So the top plot is the temperature, the air temperature, and the skin temperature of the surface. And we're relating it to the temperature changes in the subsurface that we measured. So there's some really interesting features of this plot that you could pull out if you really stared at it for a long time. But what's most interesting is you can watch things like percolation events. So if you care a lot about the Greenland ice sheet and you have this melt and you want to know where the water goes, someone in a previous talk mentioned hydrology, you can watch it percolate into the subsurface. So you can see these first melt events in the early spring, and you can watch meltwater be produced and see where it goes, which is a very exciting thing in my opinion. And then most critical aspect of this, because you can do a bit of that last slide with an automatic weather station, but the critical thing for this particular platform is we made all of those cloud measurements. So on the top, you have our laser reflectivity, and you can watch the cloud evolution overhead and how that connects to the subsurface events. And I think, yeah, I'm gonna move a little quicker so we can get some questions. And we had this ground penetrating radar, and we all did these snow pits to kind of bookend these measurements. The idea being, if you're not a research station, if you're not there year round, you need to know what the conditions were when you went in and when you left, and then that gives you a nice way to constrain the measurements in between, and we worked really hard to do that. And I think for something like IPY, that's the real challenge. You have these research stations, but let's say you install a whole lot of instrumentations in various places, contextualizing it is very, very hard. Brief slide about FAIR. We're talking about the importance of data going into places that we can all access. The WMO, I participated in a project called the OpSiteMap Europolar Prediction Intercomparison Project, and we worked very hard at making sure the real-time data that comes out of this instrumentation is usable by other folks. So, the future. My vision for the future is that you take these sorts of things and you make them plug and play, and you work very hard with other people to make sure that they're taking measurements that they're also interested in, and then you build a lot of them. So we've applied for 4 prototype grants from a couple different institutions. We were recently funded in the UK by a technology funder called ARIA and got a large chunk of money to improve on this, and I'm hoping that in the next couple of years that this is a lot of what my work will be. And I want it to be collaborative and open with anyone who is interested in talking about it. So things like open source code, how can we evaluate models in an open and fair way, and how can we bring younger folks into this type of work, so PhD positions and building institutional knowledge together so that when we get to IPY in 10 years, we actually know what we're doing and there's young people that can do it. Please reach out if you want to talk about it.
Great system. I was wondering, how do you keep it ice and rime free?
A lot of work over the last decade. The whole thing, that power plot, for example, we have a bunch of different heaters and a whole set of code base that can actually interact with specific instruments, get feedback and say, oh, this is rhymed up, turn these heaters on. And each one we've tuned over time in a way that we can actually do that. Still problems. I could talk all about how certain things didn't work perfectly, but that's a big part of the effort, is making sure that it can run and that nothing breaks in a horrific way while it's out there.
Okay, thanks.
We now have Jan René Larsen from AMAP, and he's going to talk to us about SEON. Thank you.
Yeah, thank you for this opportunity to talk about the roadmap for observing and data system, the roads process. And the background here is, as Hannah talked about, this idea of in observations you must engage, in this case, the industry. I would like to have a bit of a focus on indigenous people and local perspectives. How have we in this process worked with indigenous people? Because I'm quite sure that there will be an interest from indigenous and local people also for the IPY process. Volker has already explained a bit about the background for SEON. It was a body made up after the early IPY. Arctic Council and IASC is behind it. And the purpose was to improve observations and data systems. And in that process, we developed this roadmap for improving coordination of Arctic observing and systems. And let me just focus here on the first principle here, because that principle is about including indigenous people, and what is important in that context, also be able to fund their participation. Usually these people and organizations don't have their own capacity and resources, and our process has been a way to make sure that that could happen. But in the IPY context, it could be interesting perhaps also to take a look at the other principles of the roads process, which would be about, from the many things that you can observe, and the roads process is about prioritization, from the many things you can observe, always make sure that there is a demonstrated benefit of what you want to do. As a third principle here, knowing that there are so many existing initiatives out there, and this idea that it's not possible to invent new things without understanding and even better base yourself on existing initiatives. Our third principle here is always to complement and integrate existing systems. And then the fourth principle here is that many of these things must come as grassroots initiatives. It's rarely successful to come up with these big plans. There are always good ideas, good intentions also at the grassroots level, and make sure that any planning process that you invest in always understand the grassroots of this. So again, from the many things that you want to do, the process that we have outlined here would be about how to prioritize these. And traditionally, when you have doing these investigations or these planning efforts, you would start by saying, where do we want to go and how do we want to do measurements? The process that we have taken is more along the lines of, if we want to do observing, who is going to be involved and who will benefit from these observations. And then we'll go to the specificities of what, where, how, etc. The way we've worked with this is that we have developed a so-called advisory process, and in that process we have a panel, but even more important, we have proposal for establishing a series of expert panels, and they can either be regional, topical, or issue-driven. And each of these panels will then go through this 4-stage process where in each of the steps we have a documentation package, and we also have a review package, a review process that is driven by this advisory panel. And that first step is naturally initiated an expert panel. In the second panel, it's all about understanding the benefit of proposing a particular observable, a particular exercise to do observations. And then in the third process, and that's where we go to the actual specificity, what is it that we want to measure, where do we want to do it, what about data streams, what about data products, etc. And then the last and fourth slot here is about how do we actually do it, and that's of course also where the funding aspect comes into the question. We are happy that we are able to, this advisory panel has a very broad composition, so we don't even, we're not only having just experts from agencies, etc. We also have indigenous people, which is the focus here, but we also trying to attract funders and agencies in the nations which are actually going to do these things. So this is the process there. We currently run these 6 expert panels. Volker introduced to you the Arctic Passion Project, which is driving and funding 3 of these: permafrost, sea ice, and wildfire in a Nordic context. But then, as Volker also alluded to, we have quite good connections also to North American, in this case, Alaskan co-leads, co-workers. There's an initiative there called RNA Co-ops, and they have expert panels in wildfire, food security with focus on salmon, and then harmful algal bloom, the risks associated with that. And just an overview of how these different expert panels are now migrating through this process. And the reason why we put emphasis on this again is, from the many things you can observe, this is a process that allows you to prioritize and document the value of doing specific observables. And in the context of IPY, it could be an idea, especially if you envisage an integrated process for the definition of the IPY, to have a process similar to this where you are able to document the value of each of the things that you want to observe. And again, the importance of these expert panels and their indigenous engagement focus is here that we're always trying to make sure that there is indigenous leadership and there's a focus on co-production of knowledge. I should say that this is not easy. Indigenous people, as I said, I usually have little capacity. Many people are interested in their work, and that's why, as a first guiding principle, make sure that there is funding available for their engagement. I just want to promote that this principle, this works, is further developed during the coming Arctic Science Summit Week. As part of that, there is also the so-called ICARP IV process, which is a 10-year planning process, and it will bring us, you can think of this as a predecessor for the IPY, because we'll definitely discuss questions also of relevance for the IPY. And then, as Volker mentioned, a spin-off of this work is the Arctic Observing Summit that is held every second year and also discusses these processes. The next one is Aarhus, Denmark 26. Yeah, if you want to know more, you can either contact Sandy Starkweather, Nora, that is chairing this, or myself. I'm the secretary for SAN, but also working with the AMAP Secretariat. AMAP is one of the working groups of the Arctic Council. Yeah, thank you.
So I would like good presentation. Thank you very much. I would like to ask about the expert panel. Don't you have an expert panel for the ocean or the expert panel for sea ice cover the ocean issues?
I mentioned that the fourth principle is about grassroots efforts, so that's why we are based on people that come to us and say this is a relevant process for us. We would like to develop our expectations or our specifications through that process. So in a way, the existing panels are, you could say, the people in the room, the people that have come to us and said, we are interested in your process. But there actually is a sea ice expert panel. It is focused more on, you could say, navigation when it comes to sea ice. So it's more about understanding models for predicting sea ice, etc. But thanks for the question.
Okay, thank you very much.
I would like to mention that in the context of SAN, we actually have a team effort where we actually are looking into perhaps doing an within GOOS and IOC, there are these ideas of regionally coordinated efforts on Arctic observing, and we actually have a team that wants to develop that. It's a bit outside the scope of this, but we have a team that I could bring you in contact with in this matter. Thank you.
Okay, that was the last talk of our session, but we'll be reconvening at 11 with new conveners. Thank you to all the speakers for making your talks and presenting your talks, but coming to Tromsø, and most of all, keeping to time. If you have any questions or thoughts or comments or maybe opportunities for collaboration, please do reach out to our speakers in the half-an-hour coffee break now or send them an email. So yeah, go grab some coffee. Thank you.